Okay. So, good morning, students. Welcome to the Real Analysis live lectures. In today's session, we are going to see countability, remaining part of countability. In previous lecture, we have seen definitions, basic definitions, finite set, countable set, uncountable set, as well as we have shown set of set of integers countable, as well as uh, n cross n is countable and a cross b is countable. If a and b are countable, then a cross b is countable. These theorems we have proved. Now in today's session we have to prove. Let me write the statement. Sorry. Countable union of countable countable sets is countable. Countable union of countable sets is countable. Can you hear my voice properly?
Yes, ma'am.
Yes, ma'am.
Yeah, that is, if n's are countable, then what is countable union of n's? Union n is equal to 1 to infinity, n is also countable. This we want to prove. Okay. Now
Yes, ma'am.
proof. Since now what is given here? N's are given to be countable. So since each n is countable, its elements can be listed like A11, A12, A13 and so on.
Yes, ma'am.
Yes, ma'am.
Right? Since each n is countable, we can represent n's as follows. Like say A1 is equal to A11, A12, A13, elements of A. Na? A1 can be represented like this, A13 and so on. A2 is equal to say A21, A22, A23 and so on. What will be n then? Elements of n will be an1, an2, an3 and so on. Okay. Now what will be union n is equal to infinity? Then union n is equal to 1 to infinity. N is nothing but what? Aij, set of all Aij's, where Ij belongs to n cross n,
Yes, ma'am.
or I belongs to n and j belongs to n, or you can write order pair belongs to n cross n, right?
Yes, ma'am.
Okay. Now I want to show this union is countable. So if I want to show this union is countable, I want to define a map from this set to some countable set. Okay, either set of natural numbers or set of, up to now we know set of natural numbers, set of z, and n cross n is countable. We already proved, right? So we will define a map. So can you give me a map, bijective map from this set to some countable set? Can you define a map? Can anybody try? F from union n is equal to 1 to infinity and 2. Shall I take n cross n?
Yes, ma'am.
Yeah.
Yes, ma'am.
By which map can I define? F of elements of this is nothing but aij. And which unique image you can give? I can take ij order pair. Can I define like this?
Yes, ma'am.
Okay. Now, which is a bijective map? Clearly, it is a bijective map. Define a map by this. Now, to show this map is bijective or claim, I will claim this F is bijective. So, if I want to show it is bijective, what I have to do? First, I have to show it is 1, 1.
1, 1.
So, to show 1, 1, what I have to do? Consider two same images, right? Let aij, comma, say ALM belongs to union n is equal to 1 to infinity n, and consider their images are same. F of aij is equal to f of ALM. Then what will happen? What is f of aij? It is just order pair ij. And what is f of ALM? It is order pair L comma M. So when two order pairs are equal, they are coordinate, if they are coordinate wise same, right? J is equal to M. So what this implies? aij is nothing but ALM. Therefore, F is 1, 1. Right? Now to show this F is onto. Now to show F is onto. How to show it is onto now? How to show it is onto?
Codomain.
Take any element from codomain. Let I comma j belongs to n cross n. Can you give me pre-image? Then there exists aij belongs to union n is equal to 1 to infinity and therefore this implies F is onto, right? So therefore F is bijective map. And since F is bijective, we can say that F is bijective map, and as n cross n is countable, n cross n is countable implies union n is equal to 1 to infinity n is also countable. Is that right? So we have proved countable union of countable set is countable. Okay. So now next theorem. Set of rationals is countable. We have to prove next theorem. Set of rational numbers is countable. So how can we prove this set of rational numbers? I will write here Q. Q is countable. We want to show now set of rational numbers Q is countable. So we know that rational number can be written as m by n, where m and n belongs to z and n is greater than or equal to 1, right? For any q belongs to q, q can be expressed as, we can write q is equal to m by n, where m belongs to z and n is greater than or equal to 1, right? M and n we can write here, or n greater than or equal to 1. M comma n belongs to z and n greater than or equal to 1. Now for any n greater than or equal to 1, define n is equal to say m by n, where m belongs to z. M by n where m belongs to z. Then what can I say about, then q is equal to union n is equal to 1 to infinity n. Can I write like this?
Yes, ma'am.
Yes, because m is any integer and n is natural number, and if I take union n is equal to 1 to infinity, n is nothing but all rational numbers will be there then, right? Then clearly q is equal to union n is equal to 1 to infinity n. Now what is what I want to show? I want to show q is countable, and already I am having countable union of countable set is countable, so it is enough to show that each n is countable, right?
Yes, ma'am.
Now claim each n is countable. Now how to show n is countable? So define a map, define a bijective map f from n to, can you tell me what should I take here? Codomain, so that I will get a bijective, I can define a bijective map.
N cross
No, n is like this. N is defined like this, m by n, where m belongs to z. We already know z is countable.
Yes, ma'am.
So shall I take z there?
Yes, ma'am.
Yes, ma'am.
Define a map f by, so f of m by n is equal to, what should I take? M. If I take, is well defined a map, whether it is a well defined map, is that okay?
Yes, ma'am.
M by n will belongs to n, and I am taking only numerator part which belongs to z. So now I want to show this is a bijective map. Now my claim, or to show f is 1 1, to show f is 1 1, what should I do? Take two elements from n. Can you give me two elements from n? Any two elements from n, and consider their images are same, and show that the two elements are same. Can you give me two elements, arbitrary elements of an? What is my an? An is like this, m by n. Can you give me two elements of an?
f of m1 by n1 and f of n2 by n2.
m2 by
n2.
n1 आणि n2 पण चेंज करायचं का? n आहे, n is fixed. How will be my elements of a1? a1 चे elements कसे असतील? m by 1 where m belongs to z. a2 चे elements काय असतील? m by 2 where m belongs to z. डिनॉमिनेटर चेंज होणार नाही. a3 काय असेल? m by 3. m belongs to z. Only numerator will change. Are you getting this?
Yes.
So n चे elements काय असतील? m1 by n, m2 by n, like that.
M2 by N.
Yes. So denominator won't change. So let m1 by n and m2 by n belongs to a n, and consider f of m1 by n is equal to f of m2 by n and show that they are equal. So what is my f of m1? What is, or
m1 is
this
equal
is
to
just
m2.
m1 which is equal to m2, and this implies m1 by n is equal to m2 by n, right? Therefore f is 1 1. Now to show f is onto, f is onto, how can I show f is onto? Take any element from z. Let m belongs to z. Then can you give me a element pre-image which belongs to n?
M by N.
Then m by n will belongs to n. Therefore, or such that we can search that f of m by n is equal to m. Therefore f is onto, and hence f is bijective map. So what this shows? This implies each n is countable, or n is countable for each n, we can say, or n is countable for each n. And by above theorem, since countable union of countable set is countable, implies union n is equal to 1 to infinity, n is countable, and this implies q is countable. Is that right?
Yes,
Okay.
Yes.
Next theorem. Now we want to prove any subset of countable set is countable. Any subset of countable set is countable, or if there is or infinite subset of natural numbers is countable. If A is an infinite subset of set of natural numbers, then A is countable. Is countable. So if it is finite set, it is already countable. But if it is infinite subset of natural numbers, also we want to show it is countable. So let A be an infinite subset of n. Infinite subset of n. Now since A is not empty, by well ordering principle there exists a least element in A, right?
Yes, ma'am.
Since A is non-empty, there by well ordering principle there exists least element, say x1, say x1. Now A is an infinite set. If I remove x1, still it will be an infinite set.
Yes, ma'am.
One element if I remove from infinite set, still it will be an infinite set and it will be a non-empty set.
Yes, ma'am.
Also,
Yes, ma'am.
Yes.
A minus x1 is an infinite set which is non-empty, Therefore, again by well ordering principle, what will happen? There exists least element
Least element x2.
which is not equal to x1. Least element, say
Yes, ma'am.
x2, and which is not equal to x1. But what is the relation between x1 and x2? x1 will be less than x2 or x2 will be less than x1.
X1 is less than x2.
Then x1 must be less than x2. Now again, if I remove x2 from this above set, also A minus x1 comma x2 is non-empty and infinite set. So there exists least element, say x3, such that what is the relation between x1, x2 and x3? x1 is strictly less than x2, strictly less than x3. So by repeating above procedure, since it is an infinite set, we can have x1, x2, x3, x4 and so on. By repeating above procedure, we get x1 strictly less than x2, strictly less than x3 and so on, such that I will write here xn and then I will write less than xn less than, such that xn is the least element of which set? Which set? A minus x1, x2, xn minus 1, right? Xn minus 1. Now we show that this A minus, now my claim is A minus x1, x2, xn minus 1 is M, or now my claim is A minus x1, x2. I will write here. x1, x2, x3 is empty. Now I am claiming A minus x1, x2, x3, so on. This is empty. So if I say this is empty, then it will be countable. A will be countable.
Yes, ma'am.
Yes. So I want to prove this. So how can I prove? To prove this, suppose not. Assume it is non-empty. Suppose A minus x1, x2 and so on is suppose not empty. Then what will happen? There exists M belongs to A. There exists M belongs to A such that M is not equal to xi for some for every I. If it is not empty, there exists M belongs to A. Is that right?
Yes, ma'am.
If it is not empty, so there will exist one extra element, right? Say it is M. Okay. Now take S is equal to K belongs to all such N such that xk is strictly greater than M. Then S is non-empty as M belongs to S, right?
Yes, ma'am.
Check this. Okay. What is our relation? x1 is strictly less than x2, strictly less than x3, and so on. Okay, so and we are saying M is not equal to xi. So M must be greater than xk. Is that right? Therefore, by well ordering principle, again by well ordering principle, S has least element. Say it is N. This implies 1, 2 up to N minus 1 belongs to S or does not belongs to S? Does not belongs to S, and N belongs to S. Is that right? Are you getting this?
No, ma'am.
What is my S? Set of all K belongs to N such that xk is strictly greater than M. M पेक्षा जे xk मोठे आहे ते त्याचा इंडेक्स I am collecting. K belongs to set of natural numbers. That set I am calling as S. Are you getting this?
Yes, ma'am.
Since it is an infinite set, again by well ordering principle, it has least element, and I am calling it as that least element as N. And since n is list, 1, 2 up to n minus 1 does not belongs to S, right?
Yes, ma'am.
Because n is list. So n पेक्षा छोटे elements S मध्ये नसतील, right? So what can I say about x1, x2 up to xn minus 1? It will be strictly less than m, and xn is greater than m. So what this implies? x1 less than x2 less than xn minus 1, which is less than m, and which is strictly less than xn,
Yes, sir.
right? So since xn is the least element, since xn is the least element of a minus x1, x2 up to xn minus 1, what this implies? Xi must be less than or equal to m.
Yes, ma'am. Yes, ma'am.
Right? So which is contradiction? Which is contradiction, no?
Yes, ma'am.
Therefore what? A minus x1, x2 and so on must be empty, and this implies A is countable.
Countable.
Okay. So using this we can prove next theorem. 0, 1, interval 0, 1 is uncountable. Where? What is 0, 1? It is set of all x belongs to R such that 0 is strictly less than x, strictly less than 1. Interval. So how can I say now 0, 1 is in open interval 0, 1 is uncountable? Suppose it is countable, then now I want to prove open interval 0, 1 is uncountable. Okay. Suppose it is not, then I can list elements of 0, 1 as A11, A12, A13 and so on.
Yes, ma'am.
Okay, I want its decimal representation. Okay, so suppose 0, 1 is countable, then 0, 1 can be written as x1, x2 and so on. So we can write each xi in decimal expansion as follows. So x1 is equal to, I can write some 0.A11, A12, A13 and so on. x2 I can write 0.A21, A22, A23 and so on. x3 I can write 0.A31, A32, A33 and so on. I can write like this.
Yes, ma'am.
Elements of, because 0.5, 0.4, 0.3, all the, or 0.312, whatever elements are there between 0 and 1, there are infinitely many elements. But suppose we are saying it is countable. If it is countable, I can write x1, x2, x3 in unique decimal expansion, right? In this way. Is that right?
Yes, ma'am.
Now define
Yes, ma'am.
y is equal to 0.B11, B22, B33, where B and N is equal to 2 if A and N is not equal to 2, and 3 if A and N is equal to 2. So what this implies? What this implies? A and N is not equal to B and N for all N.
Yes, ma'am.
But y belongs to 1, 0 1 interval. And y is not equal to xn, any xn for all n, so which is contradiction. Therefore open interval 0 1 must be uncountable. Are you getting this, what we did here? First we have listed if it is countable. Suppose we assume that it is countable. So countable means we can list its elements as x1, x2, x3 and so on. So what we are doing, we are constructing a new element other than x1, x2, x3, all that elements, and we are saying we are showing it belongs to open interval 0 1. So it is not countable. Are you getting this? What we have done here? Students, are you there?
Yes, ma'am.
Yeah. Are you getting why I define y like this? Because I want to construct a new element. जिथे एन एन 2 असेल तिथे 3 घ्या तुम्ही 4 घ्या 5 घ्या whatever. If n is not equal to 2, you write 2, and here you can write 4 also.
Okay.
Then you will get another element. If you don't want like this, or you can define like this also. Or BNN you can define as 5 if ANN is not equal to 5, and 2 if ANN is equal to 5. समजलं का? फक्त एक डेसिमल पॉइंट मधला एक एलिमेंट चेंज करायचा तर आपल्याला एक नवीन एलिमेंट मिळेल. Are you getting this?
Yes. Yes, ma'am.
So which must be countable? Uncountable, sorry, uncountable. Okay. Now using this we can prove R is uncountable. Set of real numbers. Real numbers R is, what is countable or uncountable?
Uncountable.
Uncountable. We know that it is uncountable. So suppose it is countable. Then zero one must be also countable, but just now we have proved it is uncountable, right?
Yes, ma'am.
Suppose R is countable. then every subset of countable set must be countable, and but already we have 0, 1 is uncountable. Then 0, 1, which is a subset of R, is also must be countable, but which is not true, which is contradiction, or which is not true. Therefore, R must be
Uncountable.
uncountable. And last one, the set of irrationals R minus Q is what? Countable or uncountable?
Uncountable.
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 If it is countable, how can I prove this? Suppose R minus Q is countable, then R minus Q union Q also must be countable.
Yes, ma'am.
Must be countable since Q is countable. Q is countable, already proved,
Yes, ma'am.
which is contradiction. Therefore, R minus Q is uncountable. Is that okay?
Yes, ma'am.
Okay, so this completes our countability section. So any difficulties?
No, ma'am.